Multivariable Calculus, Lesson 12.5, Day 2. We are picking back up with our second part of the lesson. We left off, the video cut off, we were finding the distance between parallel planes. We decided to just arbitrarily find a friendly point on a plane. We had the plane 10x plus 2y minus 2z equals 5. We decided to choose some friendly values for y and z, namely 0, and solving for x, then we'd get 1/2. So there are infinitely many points on that plane. Right now, though, we have the point 1/2, 0, 0. Take a look real quickly, just recapping what we had done before. I'm highlighting this right now. Rather than looking at this as two planes and having the distance between them, we could say just focus in on a point on that plane, and it really turns into an older problem. It turns into the problem that we just did a few moments earlier. Take a look at the second equation of the plane here. I'm going to minus a 1. We're going to reuse this distance from a point to the plane here. Here's your A is 5, your B is 1, your C is going to be a -1. And, I'm going to take the absolute value of this 5 times 1/2 plus 1 times 0 minus 1 times 0 minus 1 in this absolute value. Down below, we'll have the square root of a squared, so that's 5 squared, plus 1 squared plus -1 squared. And down below, this is going to be 25 plus 1, that's radical 27. Multiplying by 0 will cancel out. You'll have 5/2 minus a 1, that's -2/2, so that's 3/2. So this is really 3/2 times 1 over the square root of 27, but the square root of 27, we can factor out a 3 from that. It's 3 radical 3. These 3's cancel out, and you can quickly see that the distance between these two planes would be 1 over 2 root 3. Let's take a look at this next example. We've got skew lines, and these skew lines are such that we do not have an intersection between those two lines. And in fact, we also know that the lines are not parallel. Parallel means that not only do the lines not touch, but they could also be contained in the same plane. So notice these are parametric equations for line 1 and for line 2. And really just want to jump out and show that there are two different direction vectors. For line 1, if we were to, real quickly just jump up here for line 1, our direction vector would be a 1, a 3, and a -1. For line 2, as we're looking right here, this is like 0 plus 2s. Our direction vector would be a 2, a 1, and then a 4. And these two direction vectors, I actually drew a picture of some skew lines right here, and I think you can very quickly see that what we have here is in this orange arrow, that would be line 1. You could consider that to be a direction vector. Line 2 down below is going to have a direction vector also. Maybe that's more like the pink one. You might wonder, how in the world can we get the equation, or how can we find, the distance between these two lines? Tell you what, especially since we've really been focusing in on using that equation and that formula that we have just seen right up here, the distance between a point and a plane. Well, right now you might wonder, can we get the equation of a plane here, or do you even see a plane? Kids sometimes will say, well, I don't even see a plane. I don't know what we can even begin to think about here. So, hey, take a look at this. I could say there is a plane that would contain line 1. And tell you what, it could be, imagine that I took the direction vector that we had for line 2, and imagine that we brought it up. You might think, why in the world would we ever do that? Well, you certainly may. You can always bring two vectors tail to tail. The purpose for doing that would be so that we could find a normal vector through a cross product. Look, if we took the cross product of 1, 3, -1, and if we did a cross product with 2, 1, and 4, again, you could use your calculator to work this out real fast. For the sake of time, I've already done that actually. You'd get 13, -6, and -5. So that would be this normal vector right here. And you could think, well, is there a point on this plane that we can work with? You know what? There is. If you were to look at line 1, look at this. We had a 1, -2, and a 4. We've got a 1, -2, and -4. So I could do x minus a 1, y minus -2, and then we could have z minus 4. And what am I doing here? Well, plain and simply, I'm just saying, look, we've got this point, 1, -2, and we can even imagine that writing it as a point even, 1, -2, comma, 4. Obviously, writing it up here wouldn't fit this scenario. I'm just arbitrarily writing it. That doesn't correspond to y equaling -2, but you get the idea. And if we just had some arbitrary point here, like an x, y, z, we could go with a end minus beginning, head minus tail. That's what we had. Why do we do this? This is how we get the equation of a plane. We'll do a dot product. 13, -6, -5, and we can do a dot product here of x minus 1, y plus 2, and z minus 4. And we know already that because this is a normal line, a normal vector, the dot product will be 0. So we'd get 13 times x minus 1. And plus a -6, or we could even distribute that -6, y plus 2. And then we could have a -5 times z minus 4. And have that equaling 0. And, you know, we could distribute and clean this up. You might wonder why. Why are we doing this? Well, we'll talk about that in just a moment. First of all, we could have our 13x minus 6y minus 5z. But look, we have a minus 13 and a minus 12. That's -25. Plus 20, that would be a minus 5. And set that equal to 0. Guys, right now you have the equation of a plane. Of this plane that I drew up there. Look at line 2. Line 2, I just want to highlight in green something for you. Line 2 has a point 0, 3, -3. 0, 3, and -3. Wow. So look what's happening. We'll have 0, 3, -3. Imagine that we have a point like that right here. Now I can find the distance from that point up there to the plane. And that distance will be the distance between that situation there. That would be the corresponding height. So that's the wonderful way that we can get around this. So once again, how do we work out this formula? Well, it's going to be the absolute value of ax1 plus by1 plus cz1 plus d. Well, here's your a, b, c, and d. And then down below we'll have the square root of a squared plus b squared plus c squared. So this distance, as we work this out, wonderfully, is going to be, as we just take a look here, it's going to be 13 times a 0 minus a 6 times a 3 minus 5 times negative 3 minus 5, all in absolute value. And then down here we'd have 13 squared plus negative 6 squared plus negative 5 squared. And at this point, I'm just going to write etc. Because, for the sake of the video, I want us to be able to have time to, move on. We could simplify this and get an answer, but that should be pretty straightforward, I would hope. Guys, as we're taking a look at this next example, it says the angle between two intersecting planes. The angle between two intersecting planes is the same as the angle between the normal vectors. And that's something you just want to memorize and know, and I think that can really help you out. To justify why, let's just take a quick look at a website. You could see real quickly, this picture really shows it clearly. If you have an angle of theta between two planes, look at this plane here with your normal. You know that your normal is going to make a right angle, 90-degree angle. So this angle theta, we could just say 90 minus theta. But now look at this other plane. That has a normal also. And this 90 minus theta is just a portion of that. If we take the complement of that, we'd be back at theta. What are we seeing? This angle between the two normals is theta, just as the angle between the planes is theta. So that's a quick justification. We can talk more about that real quickly. But they want you to find the angle between the two planes. Well, it's going to be the angle between the normal vectors. Well, we can do that pretty quickly, and thankfully we can do this very fast. So your first normal, I hope you're going to notice, is really the coefficients of what you have here. It's 3, -6, and -2. As we look at our second plane, N2, well, that's going to be a 2, 2, and a -2. And at this point, I do want to just tell you that you really are just finding the angle between these two vectors right now. And the way we can do that, very simply, is through the dot product. The dot product, just a nice review, N1 dot N2 is going to be the length of N1 multiplied to the length of N2 multiplied to the cosine of the angle between them. And if we can just work this out, then we'll be good to go, and we can do this quickly. The dot product, well, 3 times 2 is 6, -6 times 2 is going to be -12, and of course -2 times -2 is a 4. What's the length of N1? Well, it's going to be 3 squared plus -6 squared plus -2 squared. The Pythagorean theorem here. Likewise, what's the length of N2? Well, it's 2 squared plus 2 squared plus -2 squared. And then, of course, we'll have cosine of theta multiplied over here. So, on the left side, 6 plus -12 is -6, and -6 plus 4 is -2. And I think we're out of time.